right, so today we're going to be talking about flux at work, particularly at work in a system. When we get started here, I would like to just get an idea of what you're thinking about flux. And so here, if I could, we're going to use a Jamboard. I'm going to copy the link. I'm going to put it in chat. And if you could, let me know, what is your definition of flux in a system? It's okay to say, I don't know, haven't heard of it, or I think it might be. Feel free to have those statements. This isn't a test. And then what everyday systems do you interact with? An example that I give is a fish tank. I have a fish tank at my house. So when I feed the fish, when I change and clean the water and such, that is definitely me interacting with that system.
Which slide do you want us to use? There's like 7 of them, and some of them already have stuff on them.
Go to slide number 4. We'll be working from 4 back. The earlier ones were from elementary, and so you're with the MS and the HS at the bottom left. I do not know. That's okay to not know. So what might be some everyday systems then? I see a lot of folks thinking about wiggle room. I don't know. Flow of energy. It's flux. So NGSS talks about systems starting kind of earlier in K2, and then in the upper elementary, they start defining, parts of a system. So a system has certain parts that the whole cannot do, that, the parts of the system cannot do what the whole does, is kind of a way that they talk about how systems and they're important. And then when you get into middle, you start looking at different systems and comparing them and noticing what is not the system explaining, how does it not match? And then in high school, that's when you get to kind of the measuring, evaluating, and manipulating systems. Students' moods, that could be, fish tanks. I see a couple of fish tanks. Sky, outer space. Yep, those are all systems that you can measure fluxes in. Students, school, classroom. Yeah, thinking about more of the historical family systems and kind of sociology systems. My body, car, daily schedule, discipline system. Yeah, you could definitely measure the flux in that. Today we had a lot of reds. Awesome. Bathtub, sinks. Yep. Awesome. Our computers, the district, always changing. Oh, it's separate, but yeah. Awesome. Yeah, these are a lot of great ideas. We'll be coming back to this Jamboard a little later once we get through our lesson today. So let's hop in it over. So flux at work. So before we get in, we got a launch date for the RV Tawny. In the slides, you'll be able to find a project update, which goes to kind of the webpage with some news. Some webcam videos. The webcam videos, I find them now very important, very cool to look at. They actually welded the masts on, so it looks like a ship. They all look like ships being built, which is pretty awesome. And then here are just some cool schematics and picture of the Coriolis machine that we're hoping to have developed. All right. So a flux you may be familiar with, all of you, is the carbon cycle. And Anna, do you mind giving us your definition of flux and how you look at the carbon cycle? And also introduce yourself.
Yeah, hi everyone. My name is Anna Hughes, and as Adam said, so I am a first-year graduate student working on the Regional Class Research Vessel RCRV project, specifically with 2 sensor systems that deal with carbon dioxide. So in the system that I am looking at a small section of the carbon cycle, and specifically sort of at the lower part of this box, I'm interested in the exchange of carbon dioxide between the atmosphere and the ocean. And so I am going to be using two of the sensors on the Tani to measure carbon dioxide in the system. So one of them measures the carbon dioxide in the atmosphere and the other in the ocean. And this is to study the flux of carbon dioxide. And so in my definition of flux is a quantity that is passing through either a surface, like the surface ocean, or a unit area over a set period of time. And so I use the idea of flux to sort of study how carbon dioxide moves within the system.
So thank you very much. Is there any questions about that? I just want to get going. All right, so this lesson, we're going to talk a little bit about what flux is. We just did that. We're going to work through an example. It's a fish tank example. And then we're going to do a group activity where you'll be in breakout rooms for about 10 minutes. And then we are going to have some connections to the RCRV after this kind of little scavenger hunt here. We have a very cool video to show you at the end of this session of Anna showing us around the RDesk, which is what we have at Oregon State that's receiving and calibrating all sorts of sensors that are going to go on the RV Tani. And a big NGSS concept that we're kind of getting to is energy and matter flows and cycles and conservations in a system. That's what we're talking about with our flux. So flux, starting at the bottom with 1 and 2, is a term used to describe the amount of something passing from the surface or an area over a defined period of time. That something can be, dependent upon what system you're looking at, and we're really going to get in there. And the defined period of time is also important because we want to measure certain quantities on certain time scales to tell us something. And then it can be used to define many different things like carbon dioxide, heat, energy, volume, and mass. So we're going to do an activity where we're going to look at a system together. And the first part is going to be what goes into the system and out of the system. That gets us to that important parts of a system. What specific quantity? This is the kind of cool part because researchers really focus on specific quantities. They can't focus on everything. And we'll get to that a little later. For example, Anna, how high into the atmosphere do you measure the CO2 in the air?
Yeah, good question. I pretty much focus on just the top meter of the atmosphere that's above the surface and nothing else in order to, again, focus on the carbon dioxide specifically at this boundary.
Yeah, and then there's a certain time period. So seconds, minutes, days, weeks, months, years, we might want to look at that data. And then what can it tell us about the system? So the change over those seconds, minutes, days, or weeks, like what is the big change that we're looking for? A common example that you see in schools a lot is the potted plant example, where you have it with water, with sunlight, the next one with just water, next one with just sunlight, and then you look at the growth. What were the growing conditions of that? So that sequestering of carbon into the physical makeup of the plant is kind of the flux that you were looking at in that system. All right, here one. So what goes in and out of the system? So here's some pictures. In class, we'd envision this being, a picture of something, and then students would be able to sort cards that would be kind of the inputs or outputs or important parts of a fish tank system. There'll be some examples later that you'll be working through in a small group. So for those of you fish keepers among us, what goes in and out of a fish tank? You can unmute or you can just type it in the chat. Food and poop. Yep, food and poop. A lot of detritus, I guess. This might be the mix. Oxygen, yep, through the back. Heat, definitely. That's one that we do not want any flux in for the fish's sake. Food, ammonia. In food, out nitrates. Yes, you want to have a low level of nitrates and nitrites because that tells us that fish poop's being broken down well. Students' hands. Oh, yeah, I'm sure this goes in all the time. Probably come out with less fingers if you got a snapping turtle. All right. So then, what specific quantity do we want to learn more about? So oxygenation or acidity or like hardness of water can be really important. So we could look at those. We could look at the amount of sun. Like something I learned is that if you expose a fish tank to direct sun, you will get a lot of algae. So keep those windows closed. That's what I found out. So this is, again, we're looking at a specific quantity. So we looked at, inputs and outputs and important parts. We've kind of covered that so far. All right. The next one is, what is the defined period of time? So Ken Dickey, Mr. Dickey, or I see a lot of folks adding oxygen. What would we want to look at oxygen for a defined period of time? Oh, seeds growing. What might be, if you're looking at oxygen concentration, what would be our time scale? So fish, if the
in a day, maybe a day.
What?
Maybe a day.
Yeah.
Take the oxygen concentration over a day.
Yeah. So how does that fluctuate? And I know the ship and stuff, they do it real time. So they want to know it every second. I used to work at the Long Beach Aquarium, and their life support systems were just an ongoing graph of every sort of thing that could be in that aquarium, which is super cool. The fish poop one, and then the water quality, I change it weekly. That would be my time scale. And now let's get into, as we can kind of guess at the end of it, what can we learn by studying the flux of the quantity would be the health of the fish, maybe. How much are the fish costing me based on how much food they're eating? How much time am I spending cleaning the tank? And that can tell us that important part. So kind of we made a system, we've looked at the important ins and outs, and we thought about what we want to measure on what time scale. And that gets us to looking at a flux. That is essentially what scientists do when they look at changes between, for example, with Anna, looking at the flux of carbon dioxide from the atmosphere to the ocean sea surface. All right, so here what we'll be doing is you will get a picture of a system. You will get some items to sort and add to it, and think about what goes in and out of that system, what is the specific quantity and the period of time. And these systems are, related to everyday systems, because I want to stretch your thinking and your students' thinkings about systems. The way that this will be sorted out, I'll send you a Google link to a folder where you'll have all this information in, but let's just do a quick review. The first one, so if you have short hair, short for you, I understand that many of us keep long hair, so if it's short for you, you're going to be working with the system of a basketball game. And then here's some things that you can consider. So playing, energy loss. That might relate to the food that you came, how are you preparing for this basketball game? Not playing, energy recovering. You could look at sweat and water, stops of play, score. So that is your system. What are you going to look at? What parts are important? All right. And then group 2, medium hair length. You'll be looking at the farm. So a farm system, a very classic example. And here are some things that you might be interested, like egg production, offspring, how much manure is made on that farm, fruits and vegetables. So that'll be for you to decide there. And then the long hair, you're looking at a city street. Here are some things you might want to consider on that city street example. Again, these are just 3 examples of everyday systems that you could, make and think about. When you're there, you're going to go through those same 4 questions that we did, and then we'll come back and have a share out. You'll also find arrows if you choose to add some arrows, and then some call outs and thought bubbles and stars. So you can always copy and paste and add these. The way this activity is envisioned for in-person is students would actually, be in a group, have the picture, and then kind of add things to it and talk about why they're adding them in the system. The big goal of this lesson is to use that scientific language of, because, and the claim evidence reasoning, like this is important to the system because it does this. It's important to measurement on this time scale because. So those sorts of questions about everyday systems. So now I will be adding this right here. I'm going to share it with you. And again, you'll see short hair, long hair, and medium hair. And then you're going to be in breakout rooms for about 10 minutes. And Anna and I will come popping in and around about, 2 minutes into those breakout rooms. So let me change this, editor, copy link, done. All right, here it comes. Awesome. All right, so go ahead and open those files and find your way there. And then in it, like I said, you will find all the instructions there. All right, let me get you into breakout. Cami or AJ, can you get us into breakout rooms for 10 minutes? And just 1, 2, or 3, and they can choose.
Okay, the rooms should be open.
Awesome, the rooms are open. If you can't decide where your hair's at, which one you'd like to join in, you're welcome to join one that you just feel is cool or one maybe you're unfamiliar with. Hello, hello, welcome. Thank you for coming back. I know that was quick and you just kind of get jolted, but I appreciate you all for being here. And also thank you for bearing with us. The way to share screen in breakout rooms we found was share screen, advanced sharing options, and then you can allow all participants to share their screens in the breakout room. All right, so let's get back to our presentation and get to kind of our debrief of that first activity. All right, so we can just kind of go basketball, then the city street, then the farm. So for the basketball group, the short hair group, what were you looking at as going in and out of your system?
We talked about water going in, and in a weird way, food, according to this diagram, but food would go in before and after, but you'd put water in the system before you're playing, and then during your playing, you're going to be losing the energy, so you need to refill with more food. That's why we have it in that direction. And then you're also losing the water with the sweat throughout while you're playing. We also talked about putting people on the sideline so that you could rest and gain energy from rest as well, but we ran out of time.
No problem. What was your time scale that you'd want to measure?
I would say either you could go quarters, you could even go by quarter, which is high school 8 minutes.
Awesome. And then by looking at kind of the sweat and the food, what could it tell us about the system?
I'm going to let a science person talk about that more. Somebody else from that group.
Can you repeat the question, Adam?
Oh, by looking at these ins and outs, such as the water and the food over the kind of like the quarters or length of a basketball game, what can it tell us about the system?
Well, the energy consumption depends on how many minutes are they being playing. So that that is related to the amount of water they lose, the amount of calories they are burning, and then according to that, they need to recover them, electrolytes and all that kind of stuff.
Excellent. Yeah. So that is definitely brings us through those 4 questions of what is it? What could we learn? What is the time scale? And then by adding stuff to this diagram, copying and pasting them, then you get to talk about things in kind of that evidence-based reasoning. So claim evidence reasoning. So let's go next to the city street. Let's see this one. So for the city street, who can kind of describe this system and what are the inputs and outputs?
I guess I'll speak. We sort of decided that we were going to measure commuters for the city. That would tell us something about pollution as well as about economic activity in the city.
Awesome. And what time scale would you use for that one?
Well, we were thinking for 1 week and see how the commuter traffic varies throughout the week. So we would be measuring probably by the hour for 1 week of time.
Okay, so you'd be looking at fluctuations across a day. Okay, awesome. And you already answered the fourth question. That could tell us about the pollution, economic activity, and congestion for in and out of the city. Very cool. All right, now let's get to the last example, the farm one. What is going on in this system, and can you tell us about it?
I think we realize there's a lot more natural cycles happening here. And if you can see, there's a lot of recycling within this system as well.
Yeah, so we have the fertilizer for crops, the chickens, the eggs. We have the sun, the growing. And then what kind of time scale would you be interested in studying it?
Probably seasons.
Mhm.
And optimal growing seasons, and even you could even tie in the time scale in which day and night happens as well.
Awesome. Very cool. Yeah, so there's a lot of richness in these kind of everyday systems that students might walk by, pass by, or play in at school. That is kind of good places to practice that systems thinking. Let's get back over here. This one just walks through the debrief through each question. We decided to do them in order, or you could do it by what's quantity by each if you'd like. All right, so now this is a censure scavenger hunt. You have about 3 minutes. Let's go with 3 minutes. Yeah, 3 minutes to get up and take a break, stretch your legs, and also find a sensor or write it down that's around you. So what is the sensor? What is the system? So I was not lying about the fish tank. I do have a fish tank, it's 20 gallons. And it came with an LED sensor that lets me know pretty much when there's too much particulate matter that's been built up in my filter, that it's not doing its job anymore. So, and it goes on in red. And the time scale for that one would be about every 2 to 4 weeks, it suggests, but I feel like that's maybe too long. I usually just clean the filter. So that is the system that I have, is my fish tank, and I use that LED sensor to, monitor water quality, water clarity, I guess. So take time. You got 3 minutes. I will be recording it here. Find that sensor and be prepared to talk about these 3 questions and just add it to the chat. So you got 3 minutes to find something, and then just post your response to these questions in the chat. And I will starting the session timer now. 3 minutes. So get up and get moving. You can mute your camera and mute your mic while you get up and find one. Or if you are the genius that y'all are, you might already know in your head. So could a space heater be considered a sensor? I mean, a space heater considered a system? I think so. Small appliance, definitely. I would consider a coffee maker a system. I know my Keurig beeps at me when I have to clean it. So that'd be a system. The cleaning at it would be the sensor. So definitely. And the heat pump. And then it can also probably tell you with heat pumps and heaters how much that costs. Smoke detector, yep. You have 1 minute and 20 seconds left. All right, that is our timer. Please take a moment to scroll through and see what your fellow teachers have shared. What I found interesting about this is for certain sensors in like a home system, like the carbon monoxide, like we don't want any carbon monoxide coming from somewhere into our house. So we want that flux to be like 0. And direction, it would be kind of like non-directional in that sense. Anna, do you have any thoughts on some of the examples that we've seen and how you as a researcher think about flux?
Yes, I thought a lot of these examples were really interesting. I didn't even think of it, but a lot of them, like a smoke detector in a house, security cameras, motion detectors, a lot of them get at like the idea of energy movement through a system, which is a very important flux, especially in Earth systems. So great job, everyone.
Awesome. Yeah. All right. So as I mentioned before, connecting to the RCRV, the webcams are up. They are actually pretty cool. All 3 ships have been kind of named, Macy and Dawn, the RV Gilbert Mason, RV Tawny. So you find some cool information there. And then Anna, do you mind saying a little bit about this model here of a flux you're very familiar with?
Yeah, so this is the system that I study, the system of carbon dioxide and sort of its exchange between the atmosphere and the surface ocean. So here we have CO2 molecules in the atmosphere. It's a major component, or a small component, 1% of, I guess, about the air in the atmosphere. We have a little picture of the carbon cycle up here. And then in the ocean, we know that carbon dioxide reacts with seawater, so H2O, and it forms carbonic acid, which is represented over here on the other side of the arrow. And so we have the RV Tawny here, and there are 2 main sensors that we might talk about if we have time later, but it'll show up in the video as well, that measure the amount of carbon dioxide in the atmosphere, and then another one that measures the amount of carbon dioxide in the ocean. And by knowing these 2 quantities, we can sort of study the flux within the system of carbon dioxide.
Awesome. And then here's just kind of another image of it. The differences between the 2 that you might notice is students might ask, like, well, how does it in there? What additional factors other than, you know, moving across the concentration gradient of diffusion? So things like wind, waves, that churning, all that gets into it. They call them eddies, right? Eddies are the ripples at the top, is another word used to describe how the kind of the ocean naturally mixes. And then here is our video. So Anna, do you want to say a little bit about what's going on in this video and what you're going to do?
Yeah, so this video is filmed at our desk, which is sort of the hub of where we are receiving sensors and testing them, calibrating them, and figuring out how we're going to outfit them on the vessel, on the RV Tawny, when the time comes. So in this video, I sort of talk about both of the sensor systems, one that measures the CO2 in the atmosphere and the other that measures it in the surface ocean, and describe why these are important, not just to my system, but to other systems in general. Hi everyone, my name is Anna Hughes and I'm a first-year graduate student at Oregon State University where I study ocean chemistry. Here we are today at the project warehouse known as RDesk, where we are receiving, calibrating, and testing equipment for the RCRV project. RCRV stands for Regional Class Research Vessel Project, which is the project that I am currently working on. In your activities, you have been learning about flux in different systems. Flux is a term that scientists use to describe the amount of something that is passing through a surface or unit area over a defined period of time. Flux can be used to describe many different quantities in a system, such as molecules like carbon dioxide, heat or energy, volume, and mass. I research ocean chemistry, focusing on the flux of carbon dioxide between the atmosphere and the ocean. This is a really important area of research because changes in the chemistry of the ocean are expected to impact marine ecosystems and other Earth systems. The amount of carbon dioxide in the atmosphere has been increasing over the past 50 years. This has led to an increase in the amount of carbon dioxide in the oceans. In the ocean, carbon dioxide reacts with seawater, which increases the amount of carbon dioxide in the oceans and changes ocean chemistry. This is a process that we call ocean acidification. Because the Earth is a system, we can study the flux of carbon dioxide between the oceans and the atmosphere to better understand how increases in carbon dioxide will affect ocean chemistry and impact marine ecosystems. Now I'm going to show you two of the sensors that I use to research carbon dioxide flux. This first system is known as the underway Apollo PCO2 system. It measures the amount of carbon dioxide that is in the sea surface by pumping in water from the sea surface through this tube and filtering it. The second sensor is the Picaro analyzer. This pumps in air from the atmosphere and tells us the concentration of carbon dioxide that is in the atmosphere. These sensors work together to tell us the amount and direction of carbon dioxide flux. For example, if the amount of carbon dioxide in the atmosphere is greater than that in seawater, we know that CO2 is fluxing from the atmosphere into the ocean. In reverse, if the amount of carbon dioxide in the ocean is higher than the amount of carbon dioxide in the atmosphere, we know that carbon dioxide is moving from the ocean into the atmosphere. In this example, the flux is being caused by a process known as diffusion. These are just two of the over 200 sensors that will be on the RCRV. As you can see, flux is a very important concept for scientists who study systems, particularly Earth and ocean systems. The RCRV will have over 200 sensors, providing large amounts of data and empowering scientists to study all different kinds of flux. Monitoring flux in Earth systems is very important for tracking changes in the world around us, specifically like those related to ocean acidification and climate change. In my work with RCRV, I hope that these research tools will help you and other scientists to think about the different types of flux in the systems around you, in your house, at school, or in nature. Ask yourself, what is important in this system? How can we measure the flux of it in this system? And what could be the possible positive or negative impacts if we altered that system? Keep up with the RCRV project by following us on social media.
That is the short video that we kind of have as a, you could use that as a summary or a kicking off part, but it's kind of nice because it situates those systems in the world around us that the students and youth have been thinking about, defining one that's in a home system or a system that they're more familiar with to kind of find around, and then ties it right into the project with the same concept that's being studied. One thing that's very interesting about the work that Anna does is how do you calibrate those sensors? What is your process for that? And calibrate.
Yeah, that's what I'm
getting them. You can give a definition of calibration.
Yeah, sure. No, that's sort of what I'm working on right now. It actually depends a lot on the system and the sensor that you're using. And so to calibrate it, we take known values of a gas in the atmosphere, and then we take sort of standard water samples and measure what the system reads out for those samples where we know the amount that's in there. And then we're able to sort of correct for it if the measurement differs from the measurement that we sort of know those standards to have. And that's a super important process in order to get accurate data.
And what kind of known quantities do you work with? Like what kind of gases and how do you get those to the lab?
Yeah, we're waiting for them to be delivered right now. I think they're supposed to be delivered in a week, which is very exciting because then I can actually start working with them. But we take cylinders, I guess, with just standard air, so they're balanced in regular air, and they have set concentrations of carbon dioxide. And then for the Picaro, it also measures methane as well as water vapor. So it has known concentrations for those specific gases. And then similar with the water samples. Yeah.
One other thing is, how often is the ship taking readings?
Yes. So the cool thing is that they're taking them continuously. And so by continuous, we mean every 3 minutes. It's not every second, but every 3 minutes, which in the world of ocean sciences is kind of deemed to be continuous measurements. And so every 3 minutes, the Apollo system actually pulls water continuously and then is able to actually take a measurement about every 3 minutes. And then similar to the Picaro sampler, I think that one might be able to get shorter timescales, but both of these are continuous systems to try and capture what the flux is at very high resolution. So as close to continuous as possible.
Awesome. And then next, we're just going to move back to our kind of Jamboard that we had here that we shared out. We're going to start working on slide 5. And then at the end, we're going to move to slide 6 here. There's only these 2 slides. I don't know why it goes to 8. But I'm going to ask you, what is a kid definition of flux in a system? So if a student in your class was like, I don't get the book. Like, what is an everyday definition you could tell a youth? And then also, what everyday systems do your students interact with? So if they're like, I don't know what do you mean a system? Like, they might understand different kinds of system, but what is one that you know that they definitely interact with? So let me just share this Jamboard with you, and that will get going. It is the same link, you just got to go to page 5. So if you still have that open, no worries, but I will be sending it to the chat now. Game worlds, yes, game worlds are rule-based systems. Awesome. For those of you that have already added something, I'm going to flip over on this slide. I believe you can be working on different slides than me at the same time. So I want to make sure that is possible. But how would you adapt these lessons for your club and classroom? So my idea for these lessons is the students would have kind of a picture with cards that they'd sort and add things to. In that same, going back here, you will see student resources. There's an activity and worksheet for each activity and some keywords there. This will get a formal lesson write-up. But how can I make this kind of activity more, when I go through and do my revisions, better for y'all? And also I want to add 2 distinctions, one area for, let's go with online, and one area for in person, as I know we are in this this flux. And if it's both, you can kind of put it in the middle. Let's go there. I'll put online all the way over there. And I believe now we are at our time. Anna and I will be here for a little bit if you'd like to chat. I'm going to look at the schedule to see where your next adventure is. Or if anyone here on the...
I can tell you.
Go right ahead.
So you're going to go back to the main session link that you started with this morning, and you're going to hear about dance and coding. Then you'll have 30 minutes for lunch, which is on your own. And then you'll come back to this link, the middle school, high school link, for a session at 12:10. So the next one you'll want is to go back to that main session link here. I can put it in the chat if you want to copy it before you leave. We don't.
Yeah, so the carbon cycle, it's one of seems to bridge all the grade bands is the carbon cycle. Is that something that middle and high school students that you feel isn't accurate? Is that one of the things that if you're teaching science, you generally touch on? You can put a thumbs up, thumbs down, or yeah, Julie?
Like if you're doing like integrated science and cycles, you could do that. And we also can touch on it in ecology. Of course, it depends on how much time they're actually here, because it's like, you know, and which units you have to focus on the most for the test. So.
Mm-hmm. What about in the club setting?
Well, they've all had it, so you can use that as a starting point for the clubs.
For supplement. Yeah. Okay. Makes sense.
It also depends on the time we have in the clubs too. We had to reduce our time greatly this year because of the lack of bus transportation for students.
I love Jamboard for recording things. It helps me get over my very ugly handwriting on sticky notes. And then I get to sort things into piles. So for those of you with some tech savvy, middle and high schools, I highly recommend it. It's also all anonymous, which could be helpful or not, depending on what you're sharing out. Awesome.
And the next session should be starting in 1 minute in the main room.
Yeah, so I'm going to then go ahead and stop screen sharing and have an excellent rest of your time. Daryl is super awesome. So I'm also very excited for that presentation.